welcome to another module in this massive open online course. So in this module, let us look at another fundamental property or fundamental result for the Gaussian channel, which is the capacity, characterize the capacity of the Gaussian channel. So what we are interested in doing in this module is to look at the capacity of the we will look at the capacity of the Gaussian channel. So what do we mean by a Gaussian channel? This is one of the most, as we have seen several times in this course, this is one of the most relevant, practically relevant, and so we have an input, we have an output, and what do we mean by a Gaussian channel is that the input and the output are related by the addition of white Gaussian noise. So we have y equals x plus n, where n is additive white Gaussian noise, mean equals 0 and power equals the variance equals sigma square. Okay. So this is basically the channel adds Gaussian noise or white Gaussian noise. Channel adds white Gaussian noise. This is one of the, as I have already mentioned it several times before, it is one of the most practically relevant is one of the most frequently encountered and practically relevant communication channel modes. And what do we mean by the capacity of this channel? Remember, by capacity we mean the fundamental rate at which, or the maximum rate at which information can be transmitted across this channel with an arbitrarily low probability of error. Okay. So the capacity has a fundamental relevance in communication system because it gives us, so the capacity is of fundamental relevance because capacity that gives us this is basically maximum rate of information transfer at an arbitrarily low probability of error. Okay. So we have the capacity at which we can, it is the maximum rate of information transfer at an arbitrarily low probability of error, and we have seen that the capacity from the fundamental result by Shannon is given as the maximum of the mutual information, that is given by the maximum of the mutual information, okay, which is still valid here, except, and the maximum has to be over the input probability density functions, that is we have to maximize this mutual information over input However, we have an additional constraint here, that is the input power is limited. Okay. So, what we are doing here is we are trying to find the capacity. The capacity is given by the maximization of the mutual information, correct, maximize the mutual information. However, unlike the case of the discrete sources, here we have an additional constraint for the continuous source, that the power of the source has to be limited by this quantity. Similar to a practical wireless communication scenario in which we have a constraint that the transmit power, right, each transmitter, right, for instance when you have a telephone system or when you have a mobile phone, the mobile phone for instance is limited by the battery, alright. So, there has to be a power source in any communication system, and the communication system and that power source limits the amount of power that can be used by the transmitter. So, naturally it is a very meaningful constraint, because if obviously if you can transmit an infinite power, then one can transmit at any rate that one wishes to, because if there is no power constraint, then one can in theory one can transmit an arbitrarily high power and overcome the effect of any noise. But the challenge is to overcome the limitations of noise imposed by the channel using a battery which supports transmission at a finite power or with a certain maximum power. So, that is the key aspect here. Okay. So, I have a source, or let us say I have a transmitter, correct. Transmitting a signal X. However, this is basically connected to a power source. Which supplies the power. So, this transmitter, let us say the power is P. So, my transmit power, that is has to be limited, and remember transmit power is nothing but the expected value of x square. So, the transmit power has to be limited by P. So, I have to maximize capacity. So, you would like to maximize capacity of the channel but subject to the power constraint. Maximize the capacity, but subject to the power constraint, that is the total transmit power is limited by this quantity. Okay. Now, let us proceed by doing that. Okay. Now, first, in order to do this, first realize that from our definition of mutual information, the mutual information is nothing but Hx minus Hx given y. This is the mutual information. Okay. So, this is the entropy, this is let us write it in a slightly different form. Of course, we know it is also equal to, no harm, because this is also correct. So, this is Hx minus Hx given y equals Hy minus hy given x. This is particularly convenient for us, as we are going to see shortly. This is a particularly convenient form, and hy given x, this of course hy is the differential entropy of y. You must already be familiar with these quantities. Hy given x is the differential entropy of y given x. Now if you go back and look at our channel model, y equals x plus n is Gaussian. Remember, the notation is n is Gaussian, mean equal to 0, variance equals sigma square. Now with the addition of y, now given y, basically you have Gaussian noise n. Now given x, it means x is a constant, and this constant x is being added to the Gaussian noise. So if a constant is added to a 0 mean Gaussian random variable, all it does is it simply shifts the mean, right? The mean of this Gaussian noise n is 0. The addition of this constant x simply shifts the mean to x, and the variance remains unchanged. So given x, now you have to realize this is something very important. Given x, y equal to Gaussian, mean equal to 0, variance mean is equal to x, it simply shifts the mean is equal to x, variance remains unchanged. So given x, x plus n simply shifts mean, variance, the variance remains unchanged. Therefore, if you look at y given x, this is distributed as Gaussian. Remember, n denotes Gaussian or normal, with mean x and variance sigma square. Therefore, h of y given x, the first interesting property you will observe is h of y given x is h of Gaussian source with mean x, variance sigma square. The differential entropy of a Gaussian random variable or a Gaussian source with mean and variance sigma, with a given mean and variance sigma square, we have seen it is independent of the mean. It does not depend on the mean. It is simply half log to the base 2 pi sigma square e, correct, which does not depend on the mean x. So this is a constant. So basically this is simply equal to half, depends only on the variance. In fact, to refresh your memory, we might as well look at what we have derived previously, that it is half log to the base 2 2 pi sigma square. It does not depend on the mean. We have seen that before. Does not depend on mean x. So given x, the differential entropy of y, that is the differential entropy of y given x, is simply half log to the base 2 2 pi sigma square e. Now what about h of y? Now let us look at y. Okay. So so the mutual information between x comma y now boils down to, well, it is h of y minus h of y given x, which is now h of y minus h of y given x is half log to the base 2 pi sigma square e. Now what about this quantity h of y? Before we look at y, let us look at what is y. Y equals x plus n. Let us assume that x is also 0 mean. although this, let us relax this and assume that x is also 0 mean. And further, an important property in the communication system is that the signal x and the noise y are independent, because the noise is added by the channel or at the receiver and x is the transmit symbols. Alright. So, these two arise from fundamentally different processes. One is the signal, the other is the noise, and the signal and noise, these come from different sources, correct. There are different mechanisms which give rise to the signal and noise, therefore, these two random variables are independent. Okay. So, that is not one of the fundamental assumptions. These are independent. Now, as a consequence of that, what we are going to have is that expected value of x into n, if these are independent, x and n are independent, this is equal to expected value of x into expected value of n. This is 0, this is 0, so this is equal to 0. So, this also implies that they are uncorrelated, implies signal and noise are uncorrelated. So, independence implies that signal and noise are now. Therefore, at this point, if you look at this y is equal to expected is x, well, let us look at expected y. Expected y is, of course, y is x plus n. So, this is expected x plus expected n, which is equal to 0 plus 0 equal to 0. Further, if you look at expected y square, this is equal to, well, expected x plus n whole square, which is equal to, you can simplify this as expected value of x square plus n square plus 2xn. Now, we know what is expected x square. So, this is equal to expected x square plus expected n square plus twice expected value of x comma n. Of course, these are uncorrelated. So, this is 0. Expected n square, this is equal to sigma square. Now, this is less than or equal to p, which means, remember, the source power is limited, power of the transmitter is limited, therefore, expected x square is less than or equal to p. Therefore, we have, using this and the independence between signal and noise, we obtain expected y square is less than or equal to p base sigma square. Let us denote this by sigma tilde square. So, we have the assumption that expected y square, or we have the result, not the assumption, we have the result that expected y square is less than or equal to sigma tilde square. Okay. So, that is the so now we have to maximize, remember, we have to maximize the mutual information subject to transmit power is p. We can equally frame that as subject as maximizing the mutual information subject to the received power, that is power of y being p plus sigma square, that is sigma tilde square. So, naturally, if the transmit power is p, noise power is sigma square, the maximum power received can be p plus sigma square, that is sigma tilde square. That is what I am going to do. Okay. So, I write C equal to max, well, now over, instead of f of x, choose the probability density function y such that expected y square less than or equal to sigma tilde square, maximize the mutual information y, between x and y. Now, we have already seen very interestingly this is maximum f of y subject to f of y expected y square less than or equal to sigma tilde square h of y minus half log 2 pi sigma square log to the base 2 pi sigma. Now, if you observe this is your h of y given x, this is a constant in the sense does not depend on it does not depend on y, or it does not depend on the input probability density function y. Very interestingly, h of y given x, right, h of y given x, because given x, y is simply Gaussian noise, with mean x variance sigma square. So, h of y given x does not depend on this probability, it does not depend on this quantity with respect to which it does not depend on sigma tilde, it does not depend on this. Okay. So, basically this is a constant, okay, which means the only quantity that needs to be maximized with respect to the probability density function of y is equivalently, I can write this as max f of y with respect to the probability density function of y expected y square less than or equal to sigma tilde square h of y, because this is the only quantity now that has to be maximized with respect to the probability density function of y minus this constant half log 2 pi sigma square c. So, only this needs to be maximized, because half log 2 pi sigma square e, this is a constant. So, only this needs to be maximized with respect to PDF of y. Okay. So, that is where we are currently. So, now we have to maximize this differential entropy of y, of the output y, with respect to the PDF, that is, choose an appropriate PDF which maximizes the differential entropy of this output y, but subject to the constraint that the power at the output is less than or equal to sigma tilde square, that is p plus sigma square. Now, how to perform this maximization of differential entropy subject to this power constraint is something that we will defer to the next module. Alright, so we will stop here, basically where we are trying to characterize the capacity, the maximum rate at which information can be transmitted across a Gaussian channel, that is a channel with Gaussian noise. So, we will stop here and continue in the subsequent modules. Thank you very much.